All right, this is a walkthrough of problem 3B.7, momentum, fluxes, and creeping flow in a slot. So basically it gives you these equations, and there's basically just a bunch of individual problems. So these equations here are just for like this region here, and these equations are like for like this region around here. So yeah. The first part of the problem. Find the components of the convective momentum flux, rho VV, inside and outside of the slot. So this is pretty simple. So you just take, rho VV, the only possible options for that are rho VX VY, rho VX VX, or rho VY VY, and that's because VZ equals 0. So those are the only options. And so you basically just multiply rho by Vx twice, and you get this. Multiply rho by Vy twice, you get this. Multiply by Vx and Vy individually, you get this. All right, so that's pretty simple. Part B. Part B is evaluate the x-axis components and the rho VV at x equals negative a, y equals 0, and x equals negative a, y equals positive a. So just back to those equations, you're just plugging them in. Like you're just plugging in negative a for x, 0 for y, and then a for x and 0 for y into the equation. So for rho v x vx at x equals negative a and y equals 0, you have this equation. I'm just plugging in negative a for x, y for 0, plug and play. Simplifies to a to the 6 over a to the 8, and that simplifies over to 1 divided by a to the 2nd. So that's where you get that equation. Doing the same for x equals negative a, y equals positive a. Again, plug them in. Same thing as last time. You get negative 1 divided by 64. No, it's 16. Negative 1 divided by 16, a to the 2nd. And there's the negative sign. That's where the negative sign comes from. Yeah. So that's B and C right there. So you just plug in, checking pretty much for B and C. Pretty simple. D does the total flow of kinetic energy through the plate. Plane x equals negative a equal the total flow of kinetic energy through the slot. So this is kind of a more complicated problem. So you're going to have to kind of like look through the textbook for like what the heck is it even talking about. So I just did Control F and I like looked up kinetic. Let's spell kinetic energy. All right, so this is the thing that I found. Like there's a bunch of random stuff just throughout the book. Obviously 39 things, but you just got to kind of look and see what's up. So this says energy may be transported in a bulk motion fluid. That's the same as our case. Fluid is going into the crevice. We show 3 mutually perpendicular elements of the area ds. So our system is 3-dimensional, so that also applies at the point P, where the fluid velocity is v, capital V, and that's in Cartesian. The volume rate of flow across the surface element ds is perpendicular to the x-axis. And so we have the x-axis, and the x-axis is in the direction of the flow as well. So ds is also perpendicular to the flow and the x-axis. So Vx ds. So the rate of energy being swept across the surface element is then this equation. So this rho times the u is internal energy, so you can cross that term out. And so you're left with this. And then 1/2 rho v squared equals 1/2 rho vx squared plus vy squared plus vz squared, and then vz is obviously 0. So we get, basically you insert this into here, vx ds, and then you want to integrate that over the surface so you can get the total kinetic energy over the surface. It's asking for the total kinetic energy, right? Total flow of kinetic energy. So that's why you're integrating over the surface. So yeah, basically just say the same things here again. Canceling out the internal energy because we're not looking for that, and integrating over this expression to get the total energy. Yeah, just say that again. And since the problem does not specify a specific velocity direction, we'll assume none of them cancel out. So yeah, we just have to do both Vx and Vy. We have to plug both of those in. I've seen answers where they just do Vx, but yeah, I do Vx and Vy here because you just got to plug them both in. It doesn't say to eliminate one. So ds equals dA, and I'm just saying that because on a lot of problems you use dA, but you can just get away with not saying that. So this plane is the plane perpendicular to the flow direction, or the x direction, as you can see, as it was said earlier. Is perpendicular to the x-axis. So this is the plane perpendicular to the x-axis. And so basically you just need to find a way to like get a differential area that is going to cover this whole plane. So I got that in the y direction, I did the differential direction with respect to y. You could maybe do it with z, but that might be difficult because z is not really, it's not really a relevant variable because there's no vz velocity. And so I got delta y times w because in the problem it defines this width as w. Let's see. Defines the width as w. What is it defined as w? Okay, yeah, so, and with w in the z direction. So that's where I got w from. Yeah. So yeah, you just multiply w times delta y because that's the area of the differential. It's a rectangle. It's the area. So yeah, now kinetic energy equals this. This was ds, and now it's w dy. So that's, then the reason we're transforming that is because s is not really a variable that shows up in the velocities. So you need to get that in terms of variables that are in the velocity, and y is a variable that's in the velocity. And w is just going to be an extra variable that, I don't know, I guess you just have it there. Yeah, so there's no y bounds on the system because it just extends infinitely in either direction. So we just integrate with respect to infinity to negative infinity. So yeah, I'm just plugging in Vx. This is Vy squared, Vx squared, Vy squared, and 1/2 rho from the 1/2 rho here. And then there's the dA or ds. Factoring out the integrating terms, which is just anything that's not y, or anything that's not like that's gonna be like multiplied or like added to y. Like, I don't know, it's just like things that you can separate from y with like multiplication or division. That's how you know that you can separate it out. Yeah, so you could put this out front of the integral here. I just don't for whatever reason. Oh wait, no, I do it right here. Yeah, and I also factor out a to the 9th to make it more simple. So again, a to the 9th, you can factor it out because it doesn't have to do with y, and you can just divide it out. So that's why you can take it out. So yeah, this integral looks really just terrible, so I just didn't do it. I did Wolfram alpha. Sorry if that's not to your standards, but yeah, that's what I did. Simplified it from there. It gave me this. I simplified it to this. And then obviously that's common denominator, so 70 pi. The pi's cancel out. This should actually be pi squared in the denominator. It shouldn't be pi cubed, sorry. Yeah, this should be pi squared in the denominator. I don't know why I didn't cancel it out. Sorry about that. I'll probably put a little thing on the screen that like corrects it. So yeah, you just combine the terms and you get this, and that's for the velocity outside of the slot. So now to find the flow inside of the slot, so this is using the other equations. This is using this equation because it's inside the slot. So we're basically just doing the same process again, but with Vx only, and this Vx, because that's the velocity profile that's like here. That's like this velocity profile. So we're just doing the same thing again. So yeah, k equals b to negative b, and that's because the y direction is now bounded by the walls b to negative b. And the final wall is, or like the larger one has to be on top. The larger number has to be on top. So that's, b is obviously bigger than negative b. So yeah, that's why it's on top. So yeah, I just take out all of the crap terms from this equation up here, just these terms, and then this is all like sorry, I was pointing at the wrong equation. All these terms, and then all of this is kind of like embedded it with y. Well, actually, yeah, it's pretty much embedded with y. So you have to keep all this the whole thing in the integral. Yeah. So yeah, I get this. And then this time I actually did the integration because it's... Oh, wait, no, I actually did Wolfram Alpha. Well, oh, yeah, because it's to the third. Yeah, I wouldn't have done that. So yeah, Wolfram Alpha. And then we're just simplifying again, canceling. Where does this row cancel out? Oh, yeah, in the denominator, I actually canceled the denominator correctly this time. There's a b to the third, b there. And then, yeah, the rows. So yeah, you get this. And then obviously, I mean, maybe you can somehow figure a way to make that equal, but I really don't think it's equal, and I didn't attempt it. So I'm going to say kinetic energy inside and outside is not the same. I mean, yeah, I don't know. If you can, there might be some algebra or something, but these are like undefined. W is like an undefined variable, or undefined static variable. This is, I think, mass flow. Yeah, I mean, it's kind of hard to prove, but just from looking at the expressions, I'm pretty sure they're not the same. All right, that's the answer for that. So part E. Part E, verify velocity distributions given in equations 3B.7-1 to 4 satisfy this dot product. So this is like this del operator is like derivatives, and then you're dotting it with all the velocities. This is like the Vxi plus Vyj plus Vzk. And so we're using these equations. Oh, wait. Oh, yeah, no, we do both of them. We do it with, sorry. We do it with these equations and these equations. So yeah, I'm pretty sure I do that. All right, again, so del operator is this. V is this. And then, so dot product, you multiply each, like this term times this term, plus this term times this term, plus this term times this term. And I dot I equals J dot J equals K dot K equals 1. So that means that there's going to be no direction variables in it. So it's just going to be like one constant term. So for the slit velocity, so I do the easier one first. So we only have the 1Vx equation. So we need to verify that the derivative equals 0, because I'm pretty sure that's what the problem asks for. Part E. Yeah, verify the velocity distributions, satisfy the relation, that equals 0. Yeah, so everything, the sum of all of the derivatives has to be 0. So yeah, in this case, there's only one equation, and since we're deriving in terms of x, and there's no x in the equation, the derivative of just a constant, so you can just treat this as a constant because there's no variable of interest to be derived, so you could just treat this as constant. So the derivative of a constant is just 0. So that just shows that the expression is 0. So now we do it with the other equations. With these equations, so we plug them in, do the derivation. So yeah, I think I just isolate. Oh yeah, so derivative rules, just look at these for deriving. Basically, just do the derivative. I don't know. Just follow the rules. Do the derivatives. Yeah, it's kind of just plug and play, blah blah blah. And we find, yeah, algebra. Woo, algebra. Divide to either side to get rid of it. So yeah, you could divide this out because it's not a variable of interest, because it's not x or y in there. And then we multiply out common denominators because, I don't know, to just make the equation simpler, I guess. So it's basically just this thing minus, or this plus this, and that is just this here equals 0. So then we're dividing out like terms, x squared plus y squared. Every single term has that, so we divide that out. We're left with this, and we multiply them out, and we cancel common terms, and we can see 0 equals 0. So yeah, for part E, that equation is valid. Del dot V equals 0. All right, so part F. Where is it? Part F. Man, this problem is long. Find the normal stress tau xx at the plane y equals 0, and also on the solid surface x equals 0. So this is just tau xx is just negative 2u dvx dx. And if you look in table B1 that's in the appendix, you'll see that it says this plus like extra terms, but those extra terms only exist if it's a non-Newtonian fluid. And like if you look in that table, like in the bottom, it like says the term goes to 0 if it's a non-Newtonian fluid, and this problem says incompressible Newtonian liquid, so that's why we can eliminate those terms, because it's Newtonian. So yeah, Txx equals this. So then we just take the derivative of our earlier solved Vx term, or not earlier solved, it's already there, it's given to us. We take the derivative of Vx with respect to x. That's 3B7-2, so that's like the entrance equations. Does that make sense? Part F, entrance equations. Yeah, at the plane y equals 0. So that's y equals 0, so that's like the origin of the coordinates. So these equations are valid at the origin region near the slot entry. So like here. So yeah, using those equations makes sense. Yeah. So take the derivative with respect to x of this, using those chain rules and those quotient rules and whatever. Just do it. Again, the quotient rule is the derivative squared this. Just, yeah, look at that. And you get this. So then you insert y equals 0 and x equals 0 for the respective planes. So tx or tau xx at y equals 0 equals this, just plugging in 0 for y, 0 for y, 0 for y. And you get this. So now we're doing the x equals 0 plane, plugging in 0 for x, 0, 0, 0, 0, 0. So this is just going to be 0, I'm pretty sure. Yeah, 0. So, yeah, that's those things solved. All right, now for part G. Find the shear stress tau yx on the solid surface x equals 0. Is this result surprising? And does the sketch velocity profile Vy versus x at some point A assist in understanding the result? It's in plane y equals A. Assist in understanding the result. Okay, so yeah. So now we're just going to find the shear stress. Okay, so from appendix B.1-6, you get this equation, and this is the whole equation, no exceptions or anything. So yeah, we need to find the derivative with respect to x for Vy and the derivative of Vx with respect to x. So this is these equations right here, because at x equals 0. So this is like at the entrance. Okay, so yeah, that's why we're using those equations. So yeah, just use chain rule and quotient rule. So basically that's just what I did here. I isolated took out the common -2 mass flow pi w over rho. And I didn't put that in here, but this term is supposed to also be like out here. I just didn't do that at first on accident. So yeah, this is, I don't know why this is 0. Wait, does that make sense? Oh yeah, it does make sense because it's d dy derivative of x cubed with respect to y is 0. So yeah, that's why that's 0. So yeah, now we're plugging in x equals 0 for tau yx at x equals 0. Because that's what the problem asks us for. So 0, 0, 0. So yeah, since there's a 0 here, this goes to 0. And then since this is 0, the whole term goes to 0. And then up here, this is 0, so the whole term goes to 0. And then this is 0, so the whole term goes to 0. So yeah, the solution is 0, totally. Tau yx equals 0. And then so if we look at this expression here, the velocity with respect to, the Vy velocity with respect to x equals 0, and the derivative of Vx with respect to y equals 0, because this whole expression equals 0. So, and this makes sense because if we look at this, so the top expression is Vx. This expression is Vx. The problem says sketch velocity profile Vy at some x in a plane y equals a. So does this assist in understanding the results? So yeah, that's what I did. So this one. So yeah, I set y equal to a, and I set a equal to 0.2. So for both of these Vx dy at So Vx is this green expression. So when y equals 0, there's an inflection point, and so the derivative of this green function at y equals 0 equals 0. So that tracks back to this other expression earlier. It tracks back to this expression vy dx. The derivative of vy, or is it vy or vx? The derivative of vx with respect to y equals 0. That tracks vx with respect to y equals 0, because at y equals 0 of this green line, there's an inflection point, and at the inflection point, the slope equals 0. So the derivative of vx with respect to y equals 0. And then for this red function, vy, there's also there's a max. There's a local max. So at a local max, the slope equals 0. At a local max, x equals 0. The slope equals 0. And just looking at these expressions, I just took out the w rho and the mass flow rate because they're just any like scalar value. They'll just, like, I can't really like put them in without like just having a value, so I just took them out. So that's why they're not in the expression here. Let me just plus. That's why they're not in the expression. So yeah, that's why that makes sense. Yeah, this is basically what I just said, but just like written out. If you want to read that, it's probably better than whatever explanation I just word vomited. So yeah, that's 3B7 solve problem. Have any questions? Feel free to comment. Have any want any problems solved that are like in the first 3 chapters of each section? That would be good. Any other chapters outside of those section problems that you want solved? Ask for those as well. I mean, I've done some of them. Yeah. Have a good day. Bye-bye.